Welcome to today's deep dive. We spend a lot of time analyzing the future of the energy grid.
We really do.
Yeah, debating the merits of, massive solar farms, next generation nuclear reactors, or utility scale battery storage.
Flashy stuff.
Right, exactly. But today we are looking at a massive uh, hidden energy consumer that's operating right beneath our streets, the wastewater management sector.
It's a huge topic.
It is. So, to you listening, you probably don't spend much time thinking about what happens after you flush the toilet or drain the sink. But our mission today is to explore how these massive energy draining facilities are quietly being engineered into self-sufficient green resource recovery hubs.
It's a total paradigm shift.
Completely.
Yeah.
And to guide us, we are unpacking a really comprehensive piece of source material today. The exact title of the study is Renewable Energy Integration in Wastewater Treatment Plants, a review of pathways to energy self-sufficiency and sustainability.
And it's a critical piece of engineering research. What is fascinating here is how it treats municipal wastewater. Not as a liability to be mitigated, but as an untapped utility.
Yeah.
Historically, municipal engineering has viewed sewage purely as a public health hazard. Get it away from people, clean it, dump it. But this study looks at the underlying chemistry and thermodynamics, framing the modern treatment plant as a localized energy and resource mine.
Which is wild. And looking at the baseline data in this study, that shifting perspective is long overdue. I mean, get this. The water management sector currently consumes roughly 4% of global electricity.
4%? That is massive.
It's staggering. And for an individual treatment plant, the energy costs can make up anywhere from 2% to 60% of their total operating expenses, depending on the region.
Yeah, depending on the text they use.
Right. That is just an enormous strain on municipal budgets and local power grids.
It is, and the strain is only compounding. To understand why this matters to you, the listener, consider the sheer physical mass of the infrastructure challenge. As urbanization accelerates, the volume of wastewater is growing exponentially. I mean, in 2012, the United States produced 12.56 million tons of dry sludge.
Wow. Over 12 million tons.
And that's just the solid waste left over after treatment in one country over a decade ago.
Incredible.
And we still have massive gaps in basic infrastructure. The study notes that in Ireland, the equivalent of 40,000 people's untreated sewage still flows into rivers and seas every single day.
Just raw sewage.
Yes, simply because these centralized facilities cannot handle the capacity, or they just lack the capital to operate effectively.
Okay, let's unpack this. Because to solve an energy drain of that magnitude, we really need to understand exactly where the power's going.
Right.
Reading through the process breakdown in this study, a wastewater plant operates a lot like an incredibly complex, energy-hungry digestive system. Water flows in, gets mechanically separated, biologically broken down, and chemically stabilized.
That's a great analogy.
But the energy distribution across those stages is wildly uneven, right?
Highly uneven. The preliminary and primary stages are actually relatively passive.
Okay.
This is where you screen out large debris, sticks, rags, grit, and then you let the water sit in primary clarifiers.
These are just big tanks.
Essentially, yes.
Yeah.
Massive settling tanks.
Yeah.
Where gravity pulls the suspended solids to the bottom. Because gravity is doing the heavy lifting there, these initial stages account for less than 1% of the plant's total energy demand.
Right, so the initial screening is just basic physics. The real energy vampire, the stage that pulls massive wattage from the grid, is the secondary treatment.
Exactly.
This is the biological phase where plants use bacterial cultures to consume the remaining organic pollutants. And the study highlights that in certain places, like Greece, this single stage can account for roughly 72% of a plant's entire energy consumption.
72%. And it comes down to the mechanics of aeration.
Right, pumping the air.
Yes. The bacteria required to break down those organics need constant oxygen to survive and reproduce. So the plant has to force massive volumes of air into these deep tanks of wastewater.
It's the giant aquarium bubbler on steroids.
Pretty much. The study looks at different configurations, like conventional activated sludge systems, which are those long, rectangular aerated tanks you often see, or oxidation ditches, which are oval channels where the water is continuously churned. Depending on the setup, this aeration process consumes anywhere from 0.8 to 1.6 kilowatt hours per cubic meter of water. You are running heavy industrial blowers and compressors 24 hours a day, 7 days a week.
Which explains the energy bill. And even after the water is clean, you are left with the sludge, the physical residual waste.
The hardest part to deal with.
Right. The study points out that managing this sludge, thickening it, dewatering it, stabilizing it for transport accounts for about 30% of a plant's total costs.
So if we connect this to the bigger picture, the immediate takeaway is that you cannot just slap a commercial solar panel array on the roof of a facility like this and expect it to go off-grid.
It's just a drop in the bucket.
Exactly. The baseline energy demand is way too high. You have to aggressively optimize the existing mechanical processes first.
Which the study actually addresses with some pretty practical upgrades. For instance, swapping out old pump controls for variable frequency drives, or VFDs.
A crucial upgrade.
Yeah, because instead of a pump running at full throttle all the time and using a mechanical valve to choke the flow, which is basically like driving with your foot on the gas and the brake at the same time.
Right.
A VFD allows the pump's motor to scale its speed to match the exact flow of water. That one change can cut pumping energy by 50%.
It's huge.
And the study also mentions deploying industrial heat pumps to capture the ambient thermal energy that is naturally sitting in the wastewater itself.
Precisely. You optimize the baseline first, and then you integrate the renewable arsenal.
Right. Let's get into those renewables, because the study profiles several different approaches, and solar is obviously the most common one.
It's the most visible, certainly.
Yeah. Treatment plants usually feature large clarifier tanks and expansive building roofs, so they have plenty of unused surface area. The study profiles the As Samra plant in Jordan as a real benchmark here.
That's a great example.
They integrated standard photovoltaic panels for electricity alongside solar thermal collectors to generate heat. And by combining both, they reduced their reliance on the local power grid down to just between 1% and 3%.
That's practically off-grid.
It really is.
The As Samra facility is an excellent proof of concept, but it also highlights the core constraint of solar in industrial applications, the baseload problem.
Right, the sun goes down.
Exactly.
Yeah.
Those biological aeration tanks require continuous power. Bacteria do not go dormant when a cloud passes over or when it gets dark.
So you're looking at massive battery storage requirements to bridge the gap?
You are. To achieve true 24/7 reliability on solar alone, you have to pair the arrays with grid-scale battery systems.
Which are not cheap.
No. Modern lithium-ion configurations
Yeah.
and the emerging sodium-ion alternatives are definitely improving in energy density, but they represent a severe upfront capital cost. And furthermore, they degrade over time.
Right.
With a functional lifespan of roughly 20 years, factoring in the replacement cycles significantly alters those long-term economic models presented in the research.
Okay, so if solar requires prohibitive battery investments to cover the night shift, what about wind power? I mean, the wind blows day and night.
It does.
But looking at the data here, the study found almost zero dedicated wind-only wastewater integration frameworks. Why is that?
It seems counterintuitive until you look at the geographic realities of municipal planning. To minimize the distance that millions of gallons of heavy sewage have to travel, treatment plants are usually built in or directly adjacent to dense urban or suburban centers.
Oh, which are terrible locations for commercial wind turbines.
Precisely. The wind patterns are heavily disrupted by urban topography. But more importantly, the regulatory friction is immense. Zoning laws, noise ordinances, visual impact assessments.
People don't want a massive turbine in their backyard.
Exactly. Making a 300-foot turbine legal next to a residential zone is practically impossible. So unless the treatment plant is located in a highly isolated coastal region, wind remains a supplemental afterthought in this specific industry.
Okay, so if you can't rely strictly on the sky above for solar and the wind is blocked by city zoning laws, where do you get consistent baseload power?
You have to look down.
Yes. Here's where it gets really interesting. The study pivots to geothermal energy. And the way it is applied here feels less like standard power generation and more like a massive engineering hack for the sludge problem.
It really is. Geothermal is compelling here because it provides continuous, uninterrupted thermal heat, 24/7. And as we established earlier, drying the dense, wet sludge is one of the most energy-intensive challenges a plant faces.
And the specific success story they highlight is fascinating. The small Italian island of Ischia.
A perfect storm of constraints.
Exactly. They had a severe logistical bottleneck. Being a small island with strict environmental laws, they had zero space for landfills.
Right.
So they were forced to package their wet sewage sludge and physically ship it across the sea to the mainland, which is just astronomically expensive.
That's sustainable.
But they realized they were sitting right over a geothermal fluid reservoir 180 meters underground, resting at 140 degrees Celsius.
That is seriously hot.
Yeah. So they tapped into that heat, ran it directly through their sludge drying process, and shrank the physical volume of the waste by 73%.
Amazing.
They drastically reduced their shipping costs, and they ran the excess heat through a turbine to generate electricity on top of it all. The whole system paid for itself in just over 5 years.
It is an incredibly elegant use of local geology.
But I have to push back here a little bit. Because geothermal drilling is notoriously expensive and highly localized, is the Ischia example actually a scalable framework for the rest of the world, or just a lucky geographic break for one specific Italian island?
That is the exact right question to ask. And to its credit, the study is very transparent about that limitation. Geothermal is heavily geographically constrained.
Right.
You cannot simply drill a well in any municipal district and expect to hit 140-degree fluid at a commercially viable depth. The upfront exploration and drilling costs are massive.
So Ischia is an outlier.
Ischia works because it sits on an active geothermal anomaly. For the vast majority of inland continental treatment plants, deep geothermal is just not a realistic primary solution.
Which brings us to the most viable, scalable solution detailed in the research. The secret weapon that almost every modern wastewater plant has sitting right there inside its tanks.
Biogas.
Biogas. The realization that the waste itself is the fuel. The plants literally make their own power.
Yes. Anaerobic digestion. This is the absolute bedrock of wastewater energy recovery. You take the concentrated organic sludge and pump it into sealed, heated digester tanks.
And the key word there is sealed, right? It's an oxygen-free environment, unlike the aeration tanks we talked about earlier.
Correct. Completely oxygen-free. By depriving the environment of oxygen, you encourage a completely different class of microorganisms to break down the organic matter.
And they basically burp out fuel.
Basically, yes. As these anaerobic bacteria metabolize the sludge, they produce a biogas that is roughly 50 to 70% pure methane.
Wow.
The plant captures that methane and routes it into on-site combined heat and power engines, we call them CHP units, generating both electricity for the plant and thermal heat to keep those digesters warm.
And the real-world triumphs here are impressive. The study details the Iowa wastewater treatment plant in Poland. They were running standard anaerobic digestion, but they wanted to boost their methane yield.
So they got creative.
Very creative. They established a supply chain with local farms to import poultry processing waste, mixing it directly into their human sewage sludge, a process known as co-digestion.
Yes.
By introducing that specific, high-energy organic mix, their methane production spiked, and the plant achieved a massive 98.2% energy self-sufficiency.
That's incredible. Co-digestion is incredibly effective from a chemical standpoint.
Yeah.
You are optimizing the carbon-nitrogen ratio for the bacteria so they eat more efficiently.
Though I can only imagine the local town hall meetings for that proposal. Hey, can we route a fleet of trucks carrying poultry processing waste through town every week to mix with the local sewage? The odor management and zoning negotiations alone must have been a nightmare.
Oh, the logistics are certainly complex.
Yeah.
But the economic payoff of near-total grid independence usually wins out in the end.
Money talks.
Exactly. But if you want to see the real technological ceiling of biogas, look at the SMAT Castiglione plant in Italy. They didn't just focus on making more gas, they revolutionized how they converted that gas into power.
Right, they moved away from traditional combustion engines.
Yes. Standard CHP engines burn the methane, and any combustion process is subject to severe thermodynamic losses. Heat just escapes.
Right.
The Italian plant swapped out their traditional combustion engines for high-tech solid oxide fuel cells, or SOFCs.
And how do those work?
These fuel cells do not burn the gas. They extract the electrical energy through a direct electrochemical reaction. It is vastly more efficient. By implementing these fuel cells, that plant hit 155.8% electrical self-sufficiency.
Meaning they are making over 1.5 times the electricity they actually need to run the plant.
Exactly.
They transformed a municipal cost center into a net exporter of clean power to the local grid. That is amazing.
It really is. But even with advanced fuel cells, the study makes a definitive point. Relying on any single renewable source, whether it's solar, geothermal, or biogas, leaves operational vulnerabilities.
So this raises an important question. If one renewable is good, what happens when you combine them? Because the study shows single sources usually fail to hit that true 100% independence mark.
Right, you build hybrid systems.
Okay.
The study analyzes several complex configurations designed to layer these technologies.
Hmm.
You might run solar arrays during peak daylight to handle the heavy aeration load, preserve your stored biogas to run the fuel cells at night, and perhaps utilize shallow geothermal heat pumps to maintain the ambient temperature of the digesters.
It's an ecosystem.
Precisely. The overlapping generation profiles create a highly resilient net zero ecosystem.
And that concept of overlapping systems leads us to what is arguably the most advanced engineering concept in this entire deep dive. The real aha moment for me. Multi-generations.
It's the frontier.
It is. This is where a wastewater plant fundamentally ceases to be just a waste management facility and becomes a localized circular economy factory. They aren't just cleaning water and spinning a turbine anymore.
No, multi-generation pushes the absolute boundaries of chemical engineering. The research details a few theoretical models that are incredibly sophisticated. Consider the proposed Haji Mohammadi system.
Yes, this one is mind-blowing. Walk us through the mechanics of it.
It starts with standard anaerobic digestion to generate biogas for power, like we discussed. But traditionally, after digestion, you still have leftover solid waste.
The stuff the bacteria wouldn't eat.
Right. The Haji Mohammadi model takes that leftover solid and subjects it to steam gasification.
Which is different from burning it. Let's make that clear.
Very different. Gasification involves heating the waste to extreme temperatures in a controlled environment with almost zero oxygen. Instead of combusting, the material breaks down at a molecular level into syngas, which is a mixture of carbon monoxide and hydrogen.
Okay.
The system then refines that syngas to isolate pure hydrogen gas,
Wow.
which can be sold as a premium zero-emission fuel for heavy industry or transportation.
So they are extracting pure hydrogen fuel from the residual sludge, and they don't even waste the heat from that process either.
No, not a single degree. The exhaust heat from the biogas engines is captured and routed into an ammonia water absorption cycle.
And we should define that for the listener because absorption cycles are brilliant.
They really are.
Instead of using electricity to run a mechanical compressor like you have in a standard refrigerator,
Ugh.
an absorption cycle uses a heat source to drive a chemical phase change between water and ammonia, which can be used for industrial cooling or, in this specific system design, to drive thermal water purification.
Exactly. So from one raw stream of municipal sewage, this single facility is engineered to simultaneously output electricity, hot water for district heating, pure hydrogen fuel, and highly purified fresh water, all at once.
It's like magic, but it's just really good plumbing and chemistry. And there's another multi-generation model in the study, the EFAI system. It takes a slightly different approach, effectively splitting municipal wastewater entirely.
Yes, this one is very aggressive.
The thick, carbon-rich sludge is routed to a digester to create biogas, which fires a gas turbine for electricity. Then, the exhaust heat from that turbine powers an absorption chiller to provide large-scale air conditioning, literally cooling for nearby buildings.
Right.
Meanwhile, the watery portion of the sewage is pushed through high-pressure reverse osmosis membranes to create pristine drinking water.
Fresh water from sewage.
Yes. And finally, they use a fraction of their self-generated electricity to power an electrolyzer, splitting some of that clean water to produce hydrogen and oxygen.
It is a closed-loop masterpiece on paper. Every joule of energy and every molecule of water is utilized. However, as an engineer, looking at the EFA system, you have to acknowledge the extreme fragility of that interconnectedness.
Because if one variable changes, it cascades through the whole plant, like a domino effect.
Exactly. Think about it. What happens during a week of heavy rainfall when the incoming sewage is highly diluted?
The organic concentration drop.
Yes. So the biogas yield drops. That means the gas turbine output drops, which means your exhaust heat drops, completely stalling your absorption chillers. Suddenly, your facility isn't producing the air conditioning or the hydrogen it contracted to provide to the city. Highly integrated systems are inherently sensitive to feedstock fluctuations.
So how do you actually build and operate a facility with that level of cascading complexity without it constantly failing? I mean, humans can't monitor all those variables fast enough.
We can't. The study points to a modern software solution: digital twins driven by artificial intelligence.
Tell me about digital twins.
Well, you cannot afford to troubleshoot a multi-generation plant through trial and error in the real world. Concrete and steel are too expensive. So engineers construct a digital twin. It's a perfect real-time mathematical simulation of the proposed facility.
A virtual plant.
Exactly. They use AI and machine learning to subject this virtual plant to millions of stress tests, They feed it decades of historical weather data. They simulate what happens if a local factory illegally dumps industrial solvents into the sewer lines.
Oh, that's smart.
They model real-time energy market pricing to see when it is more profitable to store hydrogen versus burning it for power. The AI learns the operational thresholds and optimizes the control logic before a single pipe is ever laid.
It's effectively a hyper-realistic flight simulator for municipal infrastructure.
That's a great way to put it.
And once you can reliably manage that complexity with AI, the study notes it opens the door to another major structural shift in how we handle water: decentralization.
Which is absolutely necessary. We've spent the last century building massive centralized mega plants, which require laying and maintaining hundreds of miles of deep, expensive underground piping just to move millions of gallons of water across an entire city.
It's highly inefficient.
Very, and vulnerable to single points of failure.
Right, a pipe breaks and the whole system backs up.
Exactly. With AI management and these scalable, renewable technologies, the study advocates for deploying much smaller, highly autonomous treatment plants distributed throughout a city.
So instead of one big plant, you have 50 little ones.
Right. A single facility sized to service just one rural area or one specific urban neighborhood. It treats the water locally, provides baseload electricity back to that specific district, captures its own heat, and dramatically reduces the need for sprawling central piping grids.
So what does this all mean? When you synthesize all the engineering models, the biochemical data, and the software integration detailed in this research, the ultimate takeaway is a complete shift in industrial philosophy. We have to stop viewing wastewater as a problem to be disposed of.
Yes.
And start viewing it as a critical, localized energy and resource mine. We have the technology to stop spending massive amounts of municipal energy to hide this stuff and instead engineer systems that extract high-value commodities from it.
It completely redefines the baseline of what urban infrastructure is supposed to do. A wastewater plant shouldn't just be a drain on the grid. It should be an active, contributing node in the local energy and resource economy.
And that is the roadmap to actual urban sustainability. Transitioning from passive energy consumers to vibrant, automated resource recovery hubs, all of the frameworks from the co-digestion logistics to the multi-generation models are meticulously detailed in today's source material. Again, the exact title of that study is Renewable Energy Integration in Wastewater Treatment Plants, a review of pathways to energy self-sufficiency and sustainability.
I will leave you, the listener, with this one final thought to mull over. If these localized, AI-driven multi-generation plants really do become the standard, if individual neighborhoods begin successfully treating their own waste, generating their own baseload power, and producing their own fresh drinking water and hydrogen fuel entirely independently, at what point does human sewage stop being a nuisance and instead become a highly sought-after commodity that cities and private companies actually compete to collect?
Now that is a localized infrastructure revolution hiding in plain sight. Thank you for joining us on this deep dive. We will see you next time.